Okay, a perfect square is the product of a rational number. What's a rational number? A number that can be written as a fraction. So it doesn't have to be a whole number. So it could be a fraction. The product of a rational number multiplied by itself gives a perfect square, or is a perfect square, which I'm going to be referring to PS, perfect square. Okay, so the product of a rational number multiplied by itself gives a perfect square. So for example, product of a rational number multiplied by itself gives a perfect square. If 7 squared equals 49, then who's the perfect square here? 49 is a perfect square. Okay, if a half squared equals a quarter, who's the perfect square? 1/4. 1/4 is a perfect square. So it's a rational number. It doesn't have to be a whole number. Okay. So it is confusing thinking of fractions as perfect squares, right? Because it's a rational number multiplied by itself always gives a perfect square, as long as it's rational. It can be written as a fraction. So if quarter, we can take the square root of a quarter equals a half. Okay, and I'll give us an actual rational number. Square roots, the square root of x is r if r squared equals x. The square root of x is r if r squared equals x. So, for example, the square root of, let's do something interesting, 81 equals 9, since 9 times 9 is 81, or 9 squared is 81, right? Since 9 squared is equal to 81, then we can say the square root of 81 is 9, right? They're opposite operations of each other. So it has to be able to, if we take the square root of the number, it's only a perfect square if it produces a rational number, a number that can be written as a fraction, or it's a whole number. So square root of 30, is 36 going to be a perfect square? Yeah, the square root of 36 is 6, and so therefore 36 is a perfect square. Square root of 49, 7, therefore 49 is a perfect square. Square root of 132 equals, that's an irrational number. Yeah, it's an irrational number. It can't be written as a fraction. So 11.489 ... So therefore it's not a perfect square. Okay? We're going to skip that chart all below and turn the page. We have a lot to get through. There's like 5 pages. What unit are you on? Page 55. 55, I think, right? Yeah. Okay. Skip. Oh, forgot to erase this. Oh well, we'll leave it up. Okay, write this down. A perfect cube. The product of a rational number multiplied by itself 3 times gives a perfect cube. So the product of a rational number multiplied by itself 3 times gives a perfect cube. So example I have is 2 times 2 times 2 equals 8. So 8 is a perfect cube. It's a number multiplied by itself 3 times produced 8. A rational number multiplied by itself 3 times produced 8. So it's 8 is a perfect cube. cube root of x is r such that r cubed equals x. So they're, again, a cube root is opposite of a cubing a number. How do we find the cube root? Math 4 on your calculator. So on your math 4, so cube root of 64 is 4. Okay. We all have that middle portion down? Not yet, okay. So while you're waiting, those 3 lines below, find the cube root of each one of those numbers. So the cube root of 8 is the cube root. So math 4 on your calculator will give you the cubic root. So are these all perfect cubes? Yeah, they produce rational numbers. Yes, it's a perfect cube. So math 4. All right, so we're going to just write down on that list. It says, I'm going to come back to that example of 729, finding out if it's a perfect square and perfect cube. Math 4, that's for typing it into your calculator to get the cubic root. Math 4. Okay. So I'm going to come back to that example. At the bottom of your page there, mine's a little different order. It says that there's 3 methods of determining the square or cube roots. One is prime factorization, which we're going to use a lot in this unit to do lots of things, not just find the square root and cube root. Another way is your calculator, which again, you probably will use a lot, punching it into your calculator. And the last is a diagram, which we're not really going to go. It's basically using the concept of volume equals. So either area equals x squared or volume equals x cubed. And then you do the opposite operation, which is square root, cube root, to find the side lengths. Okay? So what we're going to do is we're going to actually first, before we do that example with the 29, is define what a prime number is. Yes, Aaron. Wrong word. Use multiplied. So it's opposite. Only divisible by 1 in itself. But you're right on the right track. So prime numbers are divisible only by 1 and itself. Okay, it's only factors are 1 and itself. 1 and itself. So there's always 2 factors, right? 1 and itself. 2 of them. Yeah, they did. They just recently found a new one. It's huge. Like insanely huge. Did you really? I should really. That's awesome. And did he explain how he found it?
No,
oh, yeah.
This guy wasn't doing it, but this guy that was
talked about. They're crazy. It takes, and then to find the next highest one. Yeah. Okay. It can take like years of your life to determine the really large prime numbers. But okay, so let's list some prime numbers and some numbers that are not prime. Okay. So when I say factors, right? So for example, 9 can be written as 1 times 9 and 3 times 3. So is it prime? No, it's not. So let's start at the very bottom. Is 1 prime? Common thought is that 1 is prime, but it actually is not. 1 is not prime because it's 1 and itself. It'll have 2 factors. 1 in itself. I know it's 1 causing all this drama. Okay, 2. 2 is only factors. You can only go 1 times 2. That's the only way to multiply to 2. It's only factors. How about 3? Yeah, the only way to multiply to 3 is 1 times 3. How about 4? No, we can do 2 times 2. How about 5? Yes. 6. No, 2 times 3? 7. Yeah, it's prime. 8. 2 times 4, so it's not. Okay, you get the point? 11, 13, yeah, and so forth. Now, why is 2 so special? Why do you think 2 is such a cool number? He's even. He's the only even prime. 2 is the only even prime. Which, down the road, if you choose to take 20-2, you have to do proofs. Proofs are so much fun. And so, like proving does a prime number plus a prime number always equal an odd? Well, not always, because you have to think of the special cases. 2 is an even prime. Okay, now we can go back up. Now that we know our prime numbers, which is on your previous page there, and I'm going to show you how to use prime factorization to take the square root or cube root of a number and figure out if it's a perfect square or perfect cube. So prime factorization, I'm going to show you 2 methods. I'm going to show you my favorite first. I just find it's neater, so I like that. So our prime numbers are 2, 3, 5, 7, and so forth. So start with the smallest prime, 2, and will 2 go into 729? No, it's not even. Can't. So then we try 3. Will 3 go into 729? So we're going to divide it by 3. Does it go in? Yeah, so we're going to write 3 here, and it gives its backwards division. Goes in 243. So 2 won't go into that because we've already tried 2. So now we're going to try, will 3 go into it again? We're trying to break it into a product of prime numbers. So we want 729 to be a product of just prime numbers. So for example, 6 can be written as a product of primes of 2 times 3. Okay, you could go 30 is written as 2 times 3 times 5 as a product of prime numbers. Okay, so we're going to divide that by 3. Does it go in? Yes. So 3, 81. Will 3 go into 81? Try it again. We want to keep going until we get to or left with just prime numbers. It can't be broken down anymore. 27, can you divide that by 3? Yeah, it's 9. Can you break down 9? Yeah, 3, and it gives 3. So when our bottom number is a prime number, we stop. So you're actually including all of these numbers, including the bottom one. So 729 is the same thing as, that's a highlighter, put that away. Exactly. 3 times 3 times 3 times 3 times 3 times 3. Okay? So, yes. Or you could also write that as 3 to the power of 6. There's a reason why I'm writing it expanded right now. But yes, they often represent it with a power, so 3 to the power of 6. So the reason why I'm writing it like this is I'm trying to determine if it's a perfect square or perfect cube. Okay? Before we get to that, the other method for determining is a tree to making the product of primes. So we just need to find 2 numbers that multiply to 729. Any 2 numbers other than 1 and itself. So for example, I'm going to try 9. Yay, it worked. How did I know that was going to work? Okay, so I find 2 numbers that multiply to our number. And we're going to break them down as far as we can. Can you break down 9? Yeah, to what? 3 times 3. Are those primes? Yeah, so I'm going to circle them. 81, what can you break the 81 into? 9 times 9? We break down the 9s each. Yeah, they can each be 3 times 3. So again, 3 times 3 times 3 times 3 times 3 times 3. or 3 to the power of 6. So both methods work. I find this one takes up more room, but it doesn't matter. And you have to always find two numbers instead of starting, I don't know. Yeah, it's up to you. You can use either method. You've probably seen something like this before. Yeah, Amen. Yeah, it's the only prime. Yeah, we broke it down as far as we can, so 3 is the only prime that goes into 729. Yes. Okay, we'll talk about that in a second. Okay, so this one, is he a perfect square? Well, we figure out if it's a perfect square if we can take our primes and break it into two equal groups so that the numbers inside the groups are the same. Can we take the 6 3's and split them into two same groups? Yeah. So in this case, 3 cubed is 27. So 27 times 27. It's a perfect square. Right? The square root of 729 would be 27. So this is a perfect square. If we want to see if it's a perfect cube, we need to take our numbers and break it into 3 same groups. Can we distribute our 6 3's evenly to the 3 groups? Yeah. And so this, is it a perfect cube then? Yeah, and it would be 9 times 9 times 9. So the cubic root of 729 would be 9. Cool. Maybe not. Okay, we got to get going. Everyone get that down? Okay, turn your books to the next page if you are having them coiled like that. So we should be on, your next example we're going to go is you should be on this here, the 144 216. So you shouldn't be flipping pages, just next page, yeah. So I'm going to just actually move the 216 over here so we can have room. So we're going to practice prime factorizing and see if they're perfect cubes or perfect squares. So 144 does start with, what's our, oh, you're using the tree? You can either use a tree and then you can start with 12 times 12. If we're going to use I don't know, I wish I had a name for this. Tower? I like that. We're going to use the tower. We're going to start with prime numbers. Will 2 go into 144? Yeah. 144 divided by 2, 72. Sure, we're in hope it. Okay, will 2 go into 72? Yeah. 36. Will 2 go into 36? You're probably using your calculators to do this, and that's okay. We don't have much time, so I'm doing this in my head. Will 18, 2 go into 18? 9 times, and what can we do with 9? 3, and then 3. Okay, so 144 can be written as 2 times 2 times 2 times 2 times 3 times 3. So can we rearrange these numbers so that we have two things multiplied together so they're the same? How could we rearrange this? So we have 4 2's. So what do we have to do with the 4 2's? Split them up. So you're going to have 2 2's here, 2 2's here. You have 2 3's. What are we going to do? Split them up. So notice if there's an even number of every prime represented, it's going to be a perfect square because you have to split them into two groups. So if there's 4 2's and 2 3's, it's a perfect square. Okay, so perfect square. Is it a perfect cube? Can we break them into 3 groups? No. So not a perfect cube. 216. Do you want to try prime factorizing on your own? No. Okay, that's okay. We don't have much time, so I'd prefer not to. 216. Will 2 go into 216? Yeah. I think that's 108. Will 2 go into 108? That would be 54. Will 2 go into 54? Yeah, that would be 27. Will 2 go into 27? No, so which number do we go to next? Mine now? Check, you know better. No, so we go to 3. Will 3 go into 27? Yeah, 9. Will 3 go into 9? Okay, so we have 2 times 2 times 2 times 3 times 3 times 3. Now right away, how do I know this is not a perfect square? Amon? No. Ethan? There's 3 of each number. We can't break 3 into 2, right? 2 groups. But is it a perfect cube? Yeah. 2 times 3, 2 times 3 times 2 times 3. So it's a perfect cube. Right? We have a multiple of 3 of 2's and a multiple of 3 of 3's. So we can make a perfect cube. Okay. Skip this guy and this guy. You know how to enter this in your calculator? How do you enter that in your calculator? Math 4, not math 3. Math 4. Somebody was trying to do math 3 earlier and it wasn't working. Okay. Really quick, you need to memorize these. Why? Well, if I asked you to find the cubic root of a number without your calculator, there's 2 ways. We could either use prime factorization or you can memorize it. What's going to be faster? Memorizing, right? So this chart here that you have, you should have this on your study sheets. We're going to do some games and stuff. So what this means is these are all perfect squares, right? This means 6 squared is 36. These are my perfect cubes. This means 6 cubed is 216. Okay? Now, what? No, it's not in your book because I just wrote it up there in another class. It's on page 52 of your book. Okay? So you need to memorize you should already know your squares, memorize your cubes. We don't have time to really go through the rest of this stuff, but it's going to make it a lot faster when you're working with radicals. Okay, I promise you this, and I'm going to make more of an effort this year to make sure you memorize them. Yes. 4 cubed on your calculator. So to cube it, we use the hat is the easiest way. Okay, 4 hat 3 means 4 cubed. The hat means power of. Oh, cube root, math, 4. Cubic root. So 4 square root 3. Like 4th root? Oh, then you have to type your index, as long as if it's higher than 3, then push math 5. It's a little star there. So that means 4th root of, say, 64. Yeah, you will. It's right in your book. Okay, we're actually going to skip this part. These ones. The nice thing about 4th roots, can I say, it's the same thing as taking your square root twice. So what's the square root of 16? 4. What's the square root of 4? 2. That's your answer. Yeah. What's the square root of 81? 9. What's the square root of 9? 3. So the 4th root of 81 is 3. Yes. The math 3 for, yeah, you could do that to cube it. Yeah. Okay. So lowest common multiple. This is super important. Everyone pay attention. Make your list later. All right. So back in the day, it says the definition's already there for you, right? For lowest common multiple? Yeah, train of thought. Do you see that? What page? Least common multiple or lowest common multiple, same thing. Okay. So lowest common multiple or least common multiple is the least common or the smallest number that is a multiple of 2 or more numbers. So back in the day, what you would do is you would actually list the multiples of 30. So multiples are always larger. 15, 30, 45, 60, and so forth. Okay? Then you take your other number and you'd list its multiples. 36, 72, I'm going to end there because I don't want to think. And then 48, 96, and you keep going until you find the smallest number they have in common, the least common multiple, the smallest number that they have in common. All 3 of those. Will that take a while? Oh yeah. Okay, so you've done that before. There's a better method, prime factorization. Let me show you. Do you have a question? Oh, so finding the least common multiple, you would keep listing the multiples of that number until you found the one that was in common. Okay. So like, yeah, 2 and 3 would be 6. It was easier when it was small numbers, but what if it's not a small number? No, I was listing all the multiples of each of them. Okay. So let's prime factorize each one of these individuals. Okay. Carter, will 2 go into 15? Will 2 go into 15?
Yeah.
No. So which prime will? 3. And it'll give you 5. Can you break down 5, or is it prime? Prime. So 15 equals to 3 times 5. Okay, there's our first one, prime factorized. That was easy. Let's try 36. Should I call in somebody? Easy. Will 2 go into 36? Yeah, wasn't so bad, was it? You're like, no. 18 times. Will 2 go into 18? Yeah, 9 times. Will 2 go into 9? No, what will? 3 and then 3. So I'm actually going to write this product of primes with powers. So instead of writing 2 times 2, how else could you write that? 2 to the power of 2 times, instead of 3 times 3, 3 to the power of 2. Okay? And 48. You could also write 2 times 2 times 3 times 3. Yeah. There's a reason why I'm showing it this way. 2 will go into it. 24, 2 go into that. 12, 2 go into that. 6, will 2 go into that. 3. So 48 can be written as times. Don't forget the one on the bottom. Don't forget the guy on the bottom. Times 3. Okay. So when we're finding least common multiple, okay? Okay. Just making sure. So when we're finding least common multiple, we're going to take the product of, so for each prime, we want to take the highest prime. So we're going to find, or the product of the highest of, don't ask, the highest power of each prime. This is great study sheet material. The highest power, we're going to do the product of the highest power of each prime we see. So if 15 is 3 times 5, we have 36, 2 squared times 3 squared, and 48 is 2 to the 4 times 3. So we start with the first prime number. What's the smallest prime number? 2. Okay, so we see a 2 there. 2 to the power of what? What's the highest power we see for 2? 4 is the highest power. Okay, we take the highest power. You could even, okay, cross it out, or I don't know. I'm not going to do that. I'm just going to the highest power of each. 2 to the 4 times. Okay, what's the highest power? What's the next prime we see? 3, and what's his highest power? We have 1 here, 3 squared here, and 3 here. So 3 squared is the highest power. And any other primes? 5. Don't forget the guy. And his highest power is just 5 to the 1. Okay, so we have to represent each prime that we see and take the highest power of each prime. Okay, the reason why now each of these will divide into this number. Okay, everybody's represented. Okay, so what is 2 to the 4 times 3 squared times 5? 720. So 2 to the power of 4. That's how you type it in. 3 squared times 5 is 720. Okay, that would have taken you a while to figure out by listing all these numbers, right? So that's the lowest common multiple of these numbers. Crazy. Okay, one more example before the bell rings. Greatest common factor. It's always opposite, right? Because you hear least common multiple and you think the number is going to be smaller. But it's actually a larger number because you're doing a multiple, least common multiple. Yeah. Yep. I know. My favorite teacher today. I'm sorry. Welcome to life. Okay. Greatest common factor. Your notes, it says the largest integer that divides into a set of numbers. Okay, so we're talking about factors here. So back in the day, if you had smaller numbers, like say I had 6 and 12, you'd list all the factors. So 6 can be 1 times 6, 2 times 3, 12, 1 times 12, 2 times 6, 3 times 4, and then we find the largest factor in common, the greatest common factor. Okay, if the numbers are small, that's easy. Yes. Yes, tomorrow you're having a daily quiz. I know I'm your favorite. Yeah, I know, I was being sarcastic. Okay, so another way is using prime factorization. Let me show you. So we're going to prime factorize each one of these. Did you want to try prime factorizing this on your own? No? Okay, great. So divided by 2 is 42. Divide that by 2 is 21. Okay, 2 won't go in anymore. What will? 3, which will give you 7. Okay, we're not going to write it as powers when we're doing GCF. Because we're going greatest common factor, we're just actually going to circle what's in common. So now I'm going to go to the next guy and see, to do all 3 first so we can see what's in common. All right, 2 will go into 294, 147. 3, will 3 go into 147? Yes, it does. 49. What goes into 49? What prime number? 7, which gives 7. Good. 882. 441. Will 3 go into 441? How many times? 147. Hey, we've seen that before. Yeah. So what will go into 147? We can divide it by 3, which will give you 49, and then 7 and 7. Because we already seen that number. Okay, so, ouch. What is in common? So we're going to go through. What's in common? So do they each have a 2 in common? Yeah. If they had 2 2's in common, then we'd also circle those 2 2's. Okay, so we want greatest common factor. So we want what is in common with all of them. Okay? All right, 3's, do we have a 3 in common? Yeah. And do we have a 7 in common? Yes. So it's going to be the product of the primes in common. Because they didn't all have another 2 in common. So they had 1 2 in common, 1 3 in common, and 1 7 in common. So if they all had 2 2's in common, we'd circle both those 2's. So we want product of primes that are in common. You can also think of it this way. If you had it in powers, we have 2 squared times 3 times 7. 2 times 3 times 7 squared. And this one's 2 times 3 squared times 7. So if you look at the 2's, you have a 2 squared, 2, and a 2. So they only have 1 2 in common. The 3's, you have 3, 3, and 3 squared. So they only have 1 3 in common in this case. And 7 and 7 squared and 7, they only have 1 7 in common. Yeah, thank you. Okay, product of the prime numbers in common. So 2 times 3 times 7, what does that equal? 42. So that's our greatest common factor. Okay. So it's a product just of one of them. 2 times 3 times 7. Yeah, just one of them. Okay. All right, that was a lot to take in for one day. We will. I'm sorry. Some days we get tons of time to do homework. Today is the luck of the draw.